Welcome back. Today we're going to be looking at how to draw simple Lewis dot structures. So we are going to get started. This lesson is probably the most important lesson of chapter 8 because if you don't know how to draw a Lewis structure, everything else is going to be a struggle. So definitely really important concepts that we're going to see today. So when I'm referencing Lewis structures, what I'm really looking at is how those molecules are going to be drawn, showing all electrons bonding and non-bonding. So here we see a single bond between the two hydrogens. Here we see another single bond between the two chlorines, but then we also see 1, 2, 3 lone pairs around those chlorines. All right, so to help us understand how many bonds an element usually forms, it's easier to draw its dot structure and count the number of unpaired electrons within that structure. So for example, if you draw the dot structure of oxygen, oxygen is in group 6A, so it has 6 valence electrons to it. It's got 2 open electrons there. So those 2 open electrons are where it's going to be able to go and form bonds. So it will form a total of 2 bonds. Dot structure of chlorine. Chlorine is in group 7A. So chlorine is going to have 7 valence electrons around it. It's only got 1 open electron there. So that means it will form 1 bond, or just a single bond ever. Dot structure of phosphorus. Phosphorus is in group 5A. It has 5 valence electrons around it. It has 1, 2, 3 open electrons around phosphorus, so it's going to form 3 bonds. Looking at the dot structure of carbon there. Carbon is in group 4A. It has 4 open bonds to it, so carbon will always form 4 bonds. All right, so now we're going to look at the rules of writing Lewis dot structures, and I'm actually going to leave this here and go to our notes and fill these ideas in our notes. So in our notes, we have it kind of bolded off, and in this rectangle here, that's because this is a really important idea, something that you have to know, you need to know. So this is always something you're going to want to come back to, the rules for writing Lewis dot structures if you're struggling. So first, we're going to find the sum of valence electrons of all atoms in the polyatomic ion or molecule. So we're going to find the sum or the total of valence electrons. Now, we practiced this in our homework yesterday. So that's what is meant by finding the total or the sum of the valence electrons. If it is an anion, we're going to add 1 electron for each negative charge. And if it is a cation, we're going to subtract 1 electron for each positive charge. Then from the structure, we're going to decide what the center atom is. The center atom is the least electronegative element that isn't hydrogen. We're going to connect the outer atoms to it by single bonds. It's also the atom that you have the least amount of. If carbon is in the compound, then it is always going to be your center atom. So this is our example here that we're looking at, phosphorus trichloride, okay? And I don't want to erase, or I don't know why this is giving me so much trouble here. All right. So phosphorus trichloride. Phosphorus is in group 5A. It has 5 valence electrons available. Chlorine is in group 7A. It has 7, and there's 3 of them. So 3 times 7 is 21 plus 5 for a total of 26 electrons. Now, according to that second rule there, with deciding what our center atom is going to be, it's going to be phosphorus here. because phosphorus is the one I have the least amount of. So I would draw phosphorus as my center atom there. Then it says that we need to connect the outer atoms to it by single bonds. So I'm going to connect 3 chlorines to it with single bonds. All right, and then the rule says fill the octets of the outer atoms. By octets, what we really mean there is 8 electrons. Okay, remember the octet rule. All atoms will gain, share, or lose electrons in order to have a noble gas configuration or 8 valence electrons. So we're going to give our outer atoms octets. Each single bond here represents 2 electrons. So that's 2, 4, 6, 8 around that chlorine. The bottom chlorine here, that single bond here, is 2, 4, 6, 8. On this left side chlorine, we have another single bond, so that represents 2 electrons, 4, 6, 8. So now all of our outer atoms have octets. Then it says fill the octet of the center atom. So then my center atom there for phosphorus has 2, 4, 6 around it with those 3 single bonds. So if I put one more lone pair on it, it now has 8 electrons around it. Then it says the total number of electrons drawn should equal the original number of valence electrons. So let's count what we had. I'm going to count in blue here. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So there's 26 electrons shown in that structure. So then that means that this structure is correct. We are done. Now I know it can be kind of confusing since I have those blue marks in there. So I will redraw it. I was hoping it would look better, but it's not turning out that way. Okay, so it would look something like that. That chlorine there just looks really bad. Okay. Rule number 6, if you have too many electrons in your structure, we're going to have to form multiple bonds. Until it has the right amount of electrons. And hydrogen will never form a double bond. So we'll talk about hydrogen here in a second. So if we were drawing the compound HCN, hydrogen has 1 electron, carbon has 4, nitrogen has 5. So that's a total of 10 electrons in my structure. Carbon is in this structure, so as we said before, it would be our center atom. So then we would follow the rules. Draw the outer atoms to it with single bonds. Then it says give our outer atoms an octet. So on nitrogen here, I have 2, 4, 6, 8. Now hydrogen technically has its octet. Hydrogen is in period 1, energy level 1. Its electron configuration is 1s1. In energy level 1, the max amount of electrons something can have is 2. So hydrogen, if it was at 1s2, would be completely full, and that would be it. Well, it does have 2 electrons around it right now. You cannot add more electrons around hydrogen because it's not even possible. It's only an energy level 1. Max electrons at energy level 1 can have is 2. So hydrogen always has its octet with just 2 electrons. So remember that. That is unique to hydrogen only. It will always have its octet with just 2 electrons. All right, so we've got the octets of our outer atoms done. Now we have to fill the octet of our center atom. So carbon has 2, 4, 6, 8 electrons around it. So then that's done. Then it says the total number of electrons drawn should equal the number of valence electrons. So we would count. We have 2, 4, 6, 8, 10, 12, 14 electrons. 14 electrons is way too many. I'm only supposed to have 10. So this is where rule number 6 comes in. If you have too many electrons in your structure, you have to form multiple bonds until it has the right amount of electrons. By multiple bond, what I really mean is either a double or triple bond. Now, in order to do that, you're going to erase a lone pair from the two atoms in which you're going to form a multiple bond. So I'm going to erase a lone pair off of the carbon and nitrogen, and then I would go in and draw a double bond. And then I would count. So I'm going to count here in purple. 2, 4, 6, 8, 10, 12. So now I have 12 electrons in my structure, but it is still too many. So if I still have too many, that means I have to go in and erase another lone pair. So I'm going to erase a lone pair from carbon and from the nitrogen, and I'm going to draw in a triple bond now. So if I go back to count, and I'm going to count in purple again, I now have 2, 4, 6, 8, 10 electrons. So I have 10, which is what I want. That's good. But also make sure you have octets around all of your atoms. Hydrogen, we said, is good with 2 electrons. So hydrogen is good. So looking at carbon, I have 2, 4, 6, 8. And looking at nitrogen, I have 2, 4, 6, 8. So now everything has its octet. Everything has 10 electrons, and we are good. So if I kind of clean it up and draw the final picture, that's what HCN would look like. So let's go and apply these rules to a few more structures here in our notes. So we're starting with nitrogen trihydride, also known as ammonia. Nitrogen's in group 5A. It has 5 electrons available. Hydrogen is in 1A. It has 1 electron available, but you have 3 of them, so we multiply that by 3. That adds up to a total of 8 electrons. My center atom here is going to be nitrogen because that is the one I have the least amount of. Then the rule says draw your outer atoms to it with single bonds. So I'm going to draw single bonded hydrogens to it. And then the rule says give your outer atoms an octet. Remember, hydrogen has its octet with just 2 electrons. Never has lone pairs. It never forms multiple bonds. So hydrogen's good. Then the rule says give your center atom an octet. So if I look at nitrogen, it's got 2, 4, 6, and then I would put 1 lone pair on it to give it 8 electrons. And if we count, we have 2, 4, 6, 8 electrons in my structure. So then that means this one is good. We are done. Looking at bond types for this one, let's see here. Nitrogen is 3.04. Hydrogen is 2.20. That falls to be 0.84. Anything between 0.4 and 1.99 is a polar covalent bond type. So that guy there would be polar covalent. All right, looking at O2, I have 2 oxygens. So 2 times 6, because oxygen is in group 6A. That gives me 12 electrons available. I have 2 oxygen atoms. When you only have 2 atoms, you have no choice but to single bond those together or put a bond between them. So we would start off that way. And I don't technically have center atom or outer atoms. I just have atoms. So I'm going to make sure they have octets. So that single bond, remember, represents 2 electrons. So we have 4, 6, 8, 2, 4, 6, 8. And then I'm going to count and compare it to my 12 electrons. So I have 2, 4, 6, 8, 10, 12, 14 electrons. Too many. When we said that we had too many, we had to go in there and erase a lone pair. So I'm going to erase a lone pair off the oxygen. and I'm going to form a multiple bond. So I put in a double bond. Then I would count again, 2, 4, 6, 8, 10, 12. Now I have 12, so that matches, that's good. And then check your octets around your atoms. 2, 4, 6, 8 on the oxygen on the left, 2, 4, 6, 8 on the oxygen on the right. So kind of cleaning it up there because of all the counting. It would look something like that. Now, oxygen's value is 3.44. And you have 2 oxygens, so it'd be minus 3.44, which is 0. 0 to 0.39 in our chart is nonpolar covalent bond type. All right, so the next one there, C2H6. I have 2 carbons, so 2 times 4, 6 hydrogens, so 6 times 1. So we have 8 plus 6 is 14 total electrons. Now, our rule said when we're looking at center atoms, if carbon is in it, it will always be your center atom. Well, in this compound, I have 2 carbons. So I'm going to start with 2 carbons bonded to each other. If I had 3 carbons, I'd single bond all 3 to each other. If I had 10 carbons, I'd single bond all 10 carbons to each other. Carbons love to form long chains. So however many carbons you have in that structure, single bond those all together to begin with. The other thing that molecules love is symmetry. So in this compound, it has me having 6 hydrogens and just 2 carbons. So I'm going to share 3 hydrogens for each carbon. So I'm going to draw single bonded my outer atoms, 3 hydrogens to my carbons. And then the rule says give your outer atoms an octet. Hydrogen technically has its octet. It has its octet with just 2 electrons, so it's good. Then it says give your center atom an octet. So then I would make sure my center atom has an octet. So my first carbon here has 2, 4, 6, 8 electrons. My second one has 2, 4, 6, 8 electrons. So both center atoms have octets already. And then the rule says count the total electrons in your structure and make sure it matches your original amount. So I should match up to 14 electrons. 2, 4, 6, 8, 10, 12, 14 electrons. So I do have 14, which means that I am good. My structure is done. So then I would look at my carbon-carbon bond here. Carbon is 2.55 minus 2.55, so that is 0 again. Anytime I have the same 2 atoms, it's always going to be 0, and it's always going to be nonpolar covalent. For my carbon-hydrogen compound, carbon is 2.55, hydrogen is 2.20. That comes out to be 0.35 for the electronegative difference. 0.39 and lower is nonpolar covalent still. All right, last structure here is sulfur trioxide. Sulfur is my center atom. It's in group 6A, so it's got 6 valence electrons. Oxygen is, let's see here, also in group 6A. It's going to have 6 valence electrons, except I have 3 of them. So 3 times 6 is 18 plus 6. My structure will have a total of 24 electrons. Now, I think I already mentioned that sulfur is going to be our center atom because that's the one I have the least amount of. And then I'm going to outer bond my other 3 atoms, my 3 oxygens, and then I'm going to give them an octet, which means they all have 8 electrons around them. And then I'm going to give my center atom an octet. So around sulfur right now I have 2, 4, 6 electrons. So I'm going to draw 1 lone pair to give it 8. And then I count the number of electrons in my structure. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26 is too many, which means I'm going to have to go in and erase a lone pair then. I could erase the lone pair on sulfur, and then technically I could single bond that to any of those, oops, I forgot my eraser, to any of those oxygens, the one on the left, the one on the right, or the one on the bottom. So I'm going to erase the lone pair here, and I'm going to erase it to the oxygen on the right, and I'm going to put in a double bond. Again, count your electrons. 2, 4, 6, 8 around that oxygen, 10, 12, 14, 16, 18, 20, 22, 24. So we have 24 electrons drawn. Everything has an octet. Each oxygen has 8 electrons around it. So this is the correct structure. Now, just because I put the double bond on the right, and if you put it on the left, for example, that does not make you wrong. That is just leading into a new idea that we will be learning tomorrow. All right, last thing here, we would go and do our bond type. So 3.04 minus for sulfur. Oh, just kidding. This is 3.44. Sulfur is 2.58. So 3.44 minus 2.58. Of course, my calculator just died on me, because why wouldn't it? That value is 0.84. So I just did that in my head. I might be wrong, but regardless, it's above 0.40. So this is going to be a polar covalent bond type. All right, so hopefully you have all your structures drawn. We're going to go and build off of that idea tomorrow when we look at resonance, non-octet structures, and polyatomic ions.